All right, so now we're going to talk about second order methods in optimization on Riemannian manifolds. And so this in contrast to what we had previously discussed, it's like which were gradient-based methods, and in particular line search methods on manifolds. And so before we do that, it's like let me at least sort of briefly review it's like the situation on vector spaces. So the prototypical sort of second order method is the Newton method. And of course, it's like you typically know about the Newton method. It's like as a means of doing nonlinear root finding. So in the context of optimization, what happens then, of course, is that you want to look for points. It's like at which the gradient of the cost function vanishes. Okay, so this is the Newton method, which is sort of typically applied to sort of nonlinear root finding. So when applied to optimization, right, it is looking for roots of gradient of f is equal to 0, basically, right? So that's your function which you're trying to find the root of, and of course it's like the Newton method. It's like requires you to take the derivative of that function in order to basically construct its search direction. Okay, and so in essence, then the second order information you derive, it's like when the cost function involves directional derivatives of the gradient. So the second order information involves sort of directional derivatives of the gradient. And so what's going to happen is that the same way that in the first order case, in order to make sense of the gradient on a manifold, we needed to introduce some additional geometric structure, in particular the notion of a Riemannian metric, right? In order to make sense of this idea of directional gradient derivatives of the gradient, we need to introduce additional geometric structure as well, which is the notion of an affine connection. Okay, so in order to generalize this to manifolds, we need to make sense, and we need to introduce the notion of an affine connection. And let me sort of give you intuitively, it's like what this affine connection does. So if you recall, it's like this idea of Riemannian metric, it's like generalizes the notion of distances, it's like in the manifold. Okay, or generalizes the notion of distances to manifolds. And what happens, it's like when you do affine connections is the following. So if you have a gradient, that's obviously a vector field, okay, and essentially the idea is that if you want to take something like a derivative, it's like of the gradient using some sort of limit of a finite difference, then you basically have to take the difference of two vectors based at two different points on the manifold. So let me sort of draw a picture for you. So if you have a manifold, let's say M, and you have 2 points here, right, and they each have some sort of vector field associated with that, then the bottom line, if you will, is that if you want to differentiate, if you want to take the derivative, it's like of that vector field, then you have to be able to take the difference of vectors at two different points. Okay, and of course that actually takes some effort because of course the tangent spaces at the 2 points are different from each other, even in an embedded sense. So even if you were to think of this manifold as being embedded, it's like in some larger space. These spaces are not really, it's like the same. Okay, so there has to be a choice, if you will. It's like in order to say that, well, okay, I think of this vector as really being associated with some of the vector. It's like in the same tangent space as the initial one. Okay, so I have to do something like a transport, if you will, from one tangent space to the other. And the way you go about doing this is through this idea of an affine connection. Okay, so we'll go into greater detail. It's like in a little bit, but again, the bottom line, if you will, is that yeah, the bottom line, if you will, is like there has to be some additional geometric structure which is incorporated in order to make sense of this idea of directional derivatives of vector valued things. Okay, so this wasn't a problem. It's like when we were dealing with scalar valued objects, right? If you have scalars, it's like at two different points. It's like, well, there's no real need to identify them, and it's easy to take this sort of finite difference quotient and then sort of make sense of the notion of derivative. Okay, but with vector valued objects, it's like there requires some additional work. So that's sort of it's like the a quick overview of what we're going to be doing. It's like in this chapter is that we're going to talk about the Newton method. We're going to remind you of what the Newton method is. It's like where it comes from in the vector space setting. And then we're going to spend a little bit of time talking about this idea of affine connections to generalize the notion of directional derivatives of the gradient, which shows up in the Newton method. And then once you have, it's like that kind of geometric structure, we're then in a position to talk about generalizing Newton's methods, sort of the Newton method for optimization to Riemannian manifold. Okay, so let me just stop here for a minute.